very happy to see everyone here today. And let me share my screen. Yeah. Hi everyone. My name is Halyna. I'm working in Delivery Hero in Berlin, and I've been working on search for more than 2 years already. And my main point of focus here was machine learning for different kind of smart search functionality, let's say. So I was developing things like query expansion, query classification, query language identification, ML ranking systems, and also autocomplete. In terms of intersection of engineering and data science practices, I think autocomplete is the most interesting kind of model because it combines both machine learning techniques and machine learning stacked together with engineering requirements and a very heavy, I would say, frameworks that allow us to do autocomplete. And almost every system, I think for search now, it has autocomplete, but yeah, not all of the users understand how much it really influences the experience of user, because for instance, if you do better autocomplete on some websites which sells something, then most probably you will get an increase of CVR, which is the increase of conversion by some number, like immediately after you do a better version. So it will give you more profit like after you do this new model. And so before I start, I also want to mention that Delivery Hero now is hiring people also in search, I think. So we're hiring managers, we are hiring data engineers, we are hiring, I think, machine learning engineers. So yeah, feel free to check our positions. We have a very big discovery tribe. So most probably you all know how autocomplete system works and how it looks like from the user perspective. So you are typing something and the search engine, it completes your query. Ideally, a good search engine should offer you something relevant, something available. If we're speaking about some, for instance, food delivery service, like the platform that Delivery Hero develops. So this should be something that is relevant to your intent and is relevant to your needs. And it is ideally something that can offer you not only suggestion, but also a recommendation and offer you something that is probably available for purchase now or available to order or something like that. Most probably you all know about Elasticsearch, which is a search engine, I think the most popular one. We also use Elasticsearch in Delivery Hero, and it has some functionality out of the box which allows us to do autocomplete. And data can be mapped to a specific type, which is search as you type. It's called this way, and this data type during indexing is used that way by Elasticsearch, that it automatically generates several subfields. These subfields are either n-grams or char n-grams. So here you, for example, can see S, ST, STA, STR for this kind of string, for example. Here we're indexing this field movie title. These n-grams are generated from the text to find possible partial matches. It seems simple, in the idea of it, but we can immediately think about more complex use cases. For example, what if we want to suggest not to offer only prefix suggestions, but also infix suggestions? What I mean here is that, for example, we want to suggest Star Wars, for instance, when user is typing wars. So this would be infix suggestions. So we want to generate these subfields differently. Or what if the user does some misspelling? So for instance, he's not typing STR, but he's rather typing STS, and he made a misspelling. He's writing STSR. We want to understand that this was a misspelling and still suggest relevant things like Google does, for example. We want to make this suggestions personalized, and we want to make these suggestions like to be placed in a good order. And this is like another thing that we will discuss later. So like it all seems like pretty simple from like the perspective of generating these n-grams, but behind it there are a lot of questions which can be relevant for a good autocomplete system that fits users' needs. So these n-grams and char-n-grams, they are created during text analysis phase. For instance, here we see that we creating 2 grams, we creating 3 grams, and we are creating like index based on prefix. We are not creating index here using infix. And here, for example, like 3 grams, they are Star Wars episode, Wars episode, what is this? This is 7. And so on, and like 2 grams they are Star Wars episode, and so on, like the Force Awakens, and yeah, so on. And these partial sequences of words, they are indexed to match this partial text every time user types a query. So yeah, like this is the way that they generated these n-grams, but yeah, as I've said, like there are more possible ways to feed cases with misspellings, to feed cases with, for example, synonyms, and so on, to like, yeah, make it personalizable, but yeah, we will discuss it probably later. Yeah, and now let's go to a simple example. I took it from one website where it was described pretty well. This is not how you usually do it when you're working in the company. This is usually when you are playing with your local Elastic and you want like to understand like how it works. So here what we are doing is that we are creating edge and grams, which are here char-grams, char-n-grams, using standard tokenizer, and like we limited in this case like the min gram length and max gram length. So for instance, from the text star, we created this kind of n-grams, and this is just how it's calculated. And here, like, what can we do? Like, how can we extend it further and advance it further? Is that we can use a special field like search as you type, which we discussed before. We can like, this is very much similar, this put request is very much similar to creating a schema, I would say. So here we're saying that this is a mapping with properties. We can also like in our head associated with the schema, which assigns search as you type into the fields title and genre. And then the next step will be like, this is a good response from Elasticsearch. And then the next thing that happens is that we are feeding some data inside it, like inside this mapping, inside the schema that we originally created. So we are creating the index here, which is autocomplete. This is the destination. And we are taking the data from the source, which is movies here. So movies is a source index in this case. And here it's just a query like here to check this mapping that was created and to make sure that it all worked fine. And I think I should, yeah, this is the good, this is the ideal example of like what you should see as an output if everything worked fine. So here we see the type search as you type for genre, and you see type search as you type for title. For the fields like ID, it's just like a keyword field, and here is L1 field. So like we enabled this search as you type autocomplete functionality, which is based on n-grams, which are n-grams for fields genre and type. And now let's talk a bit more about like how this all works from the technical perspective on the background of Elastic, because it's actually not that hard, like, to play with Elastic, to send some requests to the server, to build some simple database and say, okay, I want to have autocomplete work in this way, that way, and so on. And you can go out of the box with Elastic and use their basic autocomplete functionality, but usually you either want to customize it, or you either want to build your own autocomplete system, which, like, for instance, what we're doing in Delivery Hero, because in many cases, like, this is not exactly what you need, and it doesn't allow you, without some additional plugins or something like that, it doesn't allow you really to customize it to meet your users' requirements, or like business requirements. So when we are thinking about an autocomplete, we can imagine some vocabulary of terms that we have that we can autocomplete our query with. So for instance, the user is typing BROC, and it can be brochure, it can be broccoli, it can be, I don't know, let's say broiler or something like that. And for instance, this is, let's say that, yeah, like, this is just a search engine like Google, and we don't know what the user is looking for, but we have like different articles, different, I don't know, indexed pages that we know are present in like our search engine, and we can autocomplete our query, our prefix query, with like either of these words. So we can go, like, the first naive approach that we can think about is to do binary search. Like, we can just take all of the words that we have that begin with BROC. We can create this vocabulary just from tokens of the articles that we have, or pages that we have. And the search time is the log of number of words in the vocabulary, because this is just a simple binary search. We are not talking about any ranking or suggestions here. It's like super straightforward. However, the next question comes is like, how can we improve it? How can we speed it up? Because we want something better than local. Prefix tree, it's a finite data structure which exploits these prefixes to speed up the completion. And words they are arranged as a tree. It's not a binary tree. It's, you see, it's unbalanced. It is without weights as well here for now. These words that we have in the vocabulary, they are arranged as a tree of nodes. And number of comparisons steps that we need for prefix is the same as number of letters in the prefix, which is obvious. So here, for example, we can start with two letters N and E, and we can either autocomplete it with need or nested. Yeah, and otherwise we can autocomplete it with nested. So this is like another example, like, of how can we go, like, from that simple binary search into like something better, into something faster, into something more optimized. But it's just like the beginning of what we can think about for a better autocomplete. So another thing that we can imagine is finite trace state transducers. I know that a lot of people had in the university course about finite automatas. Like, it's usually like a theoretical computer science course. I personally didn't have it because I was studying mathematics, but I guess it's a common course in the university based on what I've heard. And prefix tree, it's a type of this finite deterministic finite automatas. So these DFAs, shortly, they are the same as prefix trees, but they minimize the number of nodes. So make as few nodes as possible, and this is the reason they can handle common prefixes more efficiently. Minimizing the prefix tree reduces the size of data structure, which is logical, and it reduces our time, our latency, which is needed for lookup. So you can see that we are going from this big prefix tree into this small tree. And there is an algorithm for like going from this prefix tree into this minimized prefix tree. Yeah, but that's another topic. You can probably look it up. Then going to the next level, when we already have these DFAs, we can think about finite state transducers. Transducers is complex word. It's better to say it is a translation. So transducing means translating, if to say simply. They map terms to some output. So strictly saying, you receive some binary input, which is in our case is some prefix, so it can be like letters B, R, or C, and they map it into some output, which will be the integer in most of the cases. This is how it will look like in practice. So how it's implemented inside, it's usually the sorted map, which is sorted dictionary for understanding it better for people who are coming from Python. It's a sorted dictionary where args are in sorted order, like that's why it's sorted. And like the way it's assigned here, which you see here, they are assigned to args, not to nodes. This is important point. And as you traverse these arcs, you sum the outputs. So what means traversal? Traversal happens when you as you type, like you add one letter and then you traverse the next possible node, the next possible arc inside your FST. So this is technically already a WFST because it's weighted. So WFSTs are just weighted FSTs, but you can call it whatever you want. Also, here you see that not all of the arcs, they have weights, which is also fine in some cases. I think the default Lucene implementation, it assigns weights to all of the arcs, if I'm not mistaken. Yeah, but we'll talk about it later. So for example, here we can see a word pop, for example, which assigns firstly, for instance, the user is typing P, and we can go from P into O, only to O in this case. So this is the beginning, the beginning of our lookup. Then, for instance, the user is typing P, then type in O, and O is without a weight here, so it will be 0. Then again P, so the output will be 2, which is translating our letters into 2. Another example here is stop, for example. So we begin with 3. T doesn't have any weight here. Then we go to O, so we don't take the path with A, we take the path with O. It adds up to 4, and P also doesn't have a weight, so we finish with the output, which is 4. Also, you can look out, you can transduce your binary input not only to integers but to other things, but it's not relevant, I think, for now. So yeah, as I said, transducers, they are translating the context of the input into output. They associate the weight to path or arc instead of the leaf node. So this is how it's different. And now let's talk a bit about how it's implemented. So as I've said, autocomplete is a topic which is on the intersection of machine learning and I would say software engineering / data engineering, and how this is implemented in Elastic is that this is implemented in Lucene. Lucene is a framework, I think it's maintained as well by Elastic, it's an open source, but still there is this Apache Lucene framework and people who are supporting it open source, and this is the framework which is most probably used behind the majority of the things that you see, majority of search engines that are affording you to do some autocomplete and some lookups. So what we're doing here, this code is in Java, but it's also translatable to Scala. For instance, we do use Scala in Delivery Hero, and in Scala it also looks a bit nicer, but this is, I couldn't share that code, so this is just example that I found online. And so, for example, what we are doing here is that we are associating our vocabulary with some numbers. So this is an important point about where do we get these numbers, and we'll discuss it later a bit when we will talk about how do we rank our suggestions and how can we possibly do personalization and things like that. But in practice, how you do it when you want to rank your vocabulary is you either do it by frequency. For example, you have some pages, you do tokenization or some, I don't know, collocations extraction, and then you count the number of times tokens or collocations or n-grams appear. And this gives you some weights. Of course, if you have some user input, like, okay, user stands to click on this advertisement, users stand to order this food or something like that, then you can include some user signal as well. But in the simplest case, when you don't have any user signal, when you, for instance, are building some prototype just for fun, then you can just take frequencies and go with that. Because you can assume that the more frequent the term, the more probable it is that the user is looking for this n-gram for this token, for example. So like we are doing some like not very beautiful Java code here where we're creating a file dictionary. What's important here is that we are creating an object for lookup. So this WFST completion lookup, this is type of it. We are creating an instance of the object of the class WFST completion lookup. It accepts the directory as the input to it, and inside of this directory, we place this data. So here our delimiter is tab, and we just feed into this lookup this data, which is like already like formatted in the proper way. So we say that, okay, like wakeboard has weight 1, washing machine has weight 2, and so on. We are doing the build of this lookup using this file dictionary that we created when we read this data from this string, which is the data. And then we do lookup for results. Here we are certain, so we could just output, but here we are certain that lookup for WA, for example, first it is wax crayon, second is Washington Wizards basketball, then washing machine, then wakeboard. So here we see that it exactly matches the weights that we assign to this tokens. And this is how WFST practically works, is that as you type, like each time you do a keystroke or each time you like press your keyboard, the lookup object suggests you the list of the suggestions in the order where we're starting from the suggestion with the highest weight, and we give these weights into WFST completion lookup. You may ask yourself, like, why we are going with, you know, so complex ways, like, because obviously you could just write code for it, just simply do it as a simple Python function. But the trick is that this WFST completion lookup is one of the fastest ways to do autocomplete. And this is really important because next we will talk about like Lucene analyzers and more, you know, tricky, beautiful things, but they are still not as fast as WFST completion lookup. So this is, you know, one of the fastest ways to call autocomplete object, no matter, you know, if it's in Scala, if it's in Java, and like almost all the other analyzers that you can use, at least from this Lucene package, they are all slower. And like, yeah, pure WFST completion lookup gives you like the best latency for production. And here is another example where we're using fuzzy suggestion. So most probably, yeah, like you've heard that, for instance, you can enable fuzziness inside Elasticsearch. And yeah, like that's like also like what I think we're doing in some places. So the trick behind fuzziness is that we are assuming that the user can make mistakes. And the user can start typing something, but then make a mistake and then like continue with correct letters after that. So how we implement it in Lucene, we are also like, again, creating some directory because we need this object. Then we're creating a fuzzy suggester with analyzer. Analyzers, there are different analyzers. We'll also like discuss about what are the possible analyzers out there in Lucene. I think I will just mention a few of them, but I think that there are more. And here, for example, we can also not assign weights here. If we don't assign weights, then Lucene automatically thinks that all of the weights for each query for each n-gram, they are the same. And also, yeah, one more important thing is that they all need to be integers and they all need to be positive. So we are building a suggester in this case. So previously we were building a WFST, here we're building suggester using file dictionary, and we are looking up the query which is with misspelling. So this is wash, which is in German. And here we see that even though we've made this mistake, we still are suggesting queries, tokens, which may be relevant for the user, and most likely he was looking for something like this, something with CH, something with SH, like on the third and fourth position, something like that. So how this is done on the background? Yeah, this is like a bit specific thing. I also like needed to Google it up a bit and like read about it more, because usually like fuzziness is just being taken by default. Okay, we have fuzziness, it doesn't matter how it works behind it. But fuzziness is still an FST and WFST, like if we are switching to that terminology. And although we weren't specifically building WFST object in the previous case, we were still building WFST. We were just using a different call where we were calling analyzers and suggesters. So WFST for a Levenstein automation for word food, this is what is shown here on the diagram, and here it is with maximum distance too. So here on the arcs on the edges, we see the letters. And here they are using this idea that E is the number of arrows and N is the number of characters which we have consumed so far. Two arrows, if two arrows here, they mean either deletion or substitution, if I remember correctly. And here, one arrow, it means insertion. Yeah. So like this is the way we are like always constructing this automata, this FST for every case with fuzziness. Yeah, doesn't matter what maximum added distance is. We are just like adding more rows to this automata, the higher we make this maximum added distance. So for example, we type letter F. Then we just like accidentally touch our keyboard and we type not O, but we rather type I. And then we made an we made a substitution of like the word of the letter I, and we substituted the correct letter O with the letter I. Then we went like into this state. So we are in the n is the number of characters consumed. So like starting from 0, we are here starting from 0. And we made one error by now. Then, for instance, we continue correctly with O. Then again, like continue correctly with O. Then let's imagine that we made a mistake and we typed in letter, I don't know, before D we typed S. So yeah, then we went to this thing and we made like 2 errors, but it's still fine because we can still like go into the final node in this FST. And we made 2 errors on its way, yeah, but we were still able to get our scores. I think they are not assigning, yeah, they are not assigning like any numbers on the arcs here, but here would be some numbers because it's WFST as we imagine this case, and we still could like recognize what the user was typing. Yeah, and here is also a useful link because where it is explained, I think, a bit better what these arrows mean, what these arrows mean. So like it's a bit like more clear, I think, than I explained it in words because like they just show it a bit more detailed. Another thing that I was mentioning already earlier is infix suggester. So the thing with infix is that we want to be able to suggest things even when the user types something from the middle of the n-gram. For example, we are typing GL and we want to suggest water glass because like this user can still be looking for water glass. It's more relevant, for example, like for example gunban, gunban or gunpao, this is a Chinese food, and for instance user could be typing only pao because he just forgot that first part of the word, how this dish is called, but we are suggesting gunpao and we are understanding that user has just started from the second token, but like he is most probably still looking for this exact word. So how we are doing that? We are using analyzing infix suggester. We are still using the same analyzer. Yeah, but there are different types of them. And here we are using bytes again, but we could omit them as well here, I believe. And for example, here when we are looking up with, we are suggesting Washington Wizards basketball. When we are typing MA, we are suggesting werewolf mask and washing machine. Of course, it's better like to have both infix suggester and prefix suggester, and then to arrange suggestions together in the way that suggestions with higher weight, they will be higher, because most probably you will get different use cases from different users. Some of them always begin with prefix, some of them often start searching using infix. And another thing that we can talk about is synonyms, because this is also a very common thing, which also allows you to better handle your user experience if you don't have a very big vocabulary. So I was speaking that we will mention different analyzers here. I think that, yeah, the only one we'll have on the slides is this custom analyzer, but yeah, there are definitely more of them. And these analyzers, they, for example, allow you to get synonyms which you specify. For example, here they are specified in this file synonyms.txt, and you put them into this custom analyzer, which is then being used by the suggest object. Here, yeah, the code is not the most user-friendly. And then, yeah, like when, for example, someone is looking for merino, you can suggest them wool socks. But here you also need to be like careful what you are suggesting, which synonyms you are specifying, because usually this should be a very strong synonym if you really want to suggest user something, because otherwise it could just, you know, irritate people. Also, this analyzes and they allow us to do tokenization as well. I'm not sure if I have an example here, but you can specify the way you want this tokenization to happen, because, for example, for Chinese, for Arabic, it can be a bit tricky. Yeah, and you can also specify other stuff there. For example, yeah, like which kind of data preprocessing, I think you want to do. Yeah, so there is a lot of functionality. You can have a look there, but yeah, it's better to look in the documentation because I can't recall like probably any good examples right now. And we've been talking a lot already about like what are different analyzers, what are different like suggesters, how can they be used, how can it look like in the code. But we never really talked about ranking of suggestions. So you can imagine that user is typing BRO, and we don't know if it's better to start suggesting him broccoli first, or if it's better to start suggesting him broth first. I don't know, or some restaurant that begins with bro or something like that. Yeah, so ranking of suggestions is another big thing. So like first retrieval of suggestions happens, then happens the ranking of suggestions. And the ranking of suggestions, it's actually viewed as a like separate problem, because usually these things can be like kind of separate, like your retrieval can be good, but your ranking of suggestions can be bad and still can worsen your user experience. And you all probably know about like algorithms like RankNet, LambdaRank, and LambdaMart. At least you've heard about them. So these are standard ranking approaches that have been developed already quite a while ago. And they are used to rank suggestions, same as they used to rank articles or, I don't know, user results or anything that you can imagine after users' input. So RankNet, it was initially, I think, a neural network-based pairwise optimization function. And the idea there is that it learns these relevant scores by analyzing pairs of items and then updating the scores. So we are using this pairwise cost function, I believe, there. And we are looking at each pair and we are checking if like the item which should be more relevant, if it is on top, and if item which is less relevant, it's on the bottom. We're looking at each pair, and then like we calculate cost function based on the order of each of the pairs, like order of items inside of each of the pair. Yeah, and it was like kind of, I think, one of the first ideas. Yeah, how can we solve ranking problem? And Lambda rank is an advance of this RankNet, where we are using this relevance ratings with the same idea from RankNet. We're using the same idea for cost function, but the difference there is that we can use only gradient for updates of our pairs. So in order to do another iteration and rearrange our items for ranking, we are satisfied only with gradients that we have, and it is based on the concept of maximizing the change in the list NDCG scores. We will talk about what is NDCG a bit later, but we are scaling cost function, which is common from RankNet, using NDCG scores, which obviously makes it better, because NDCG is the metric which basically helps you understand how relevant your ranking is, your whole ranking of some items is. Yep. And going to LambdaMart, it's a list-wise optimization function that combines the advantages of like point-wise, pairwise optimization. So before we were talking about pairwise optimization. So we are using gradient descent for it to learn these relevant rankings by taking like both things, by taking scores of individual items in the list and relative ordering of the items in the list in their pairs. So we are taking into account these two things. And as far as I remember, if I am correct, LambdaMart, it is also using boosted regression trees, at least how it's implemented right now. Yeah, so so this is boosted regression trees, and there is a forest, I believe, boosted forest of this regression trees. And now let's go to metrics. This is the final part, I believe, of what we are talking about. Yeah, we're at 40 minutes now, so we're good on time. And speaking about metrics, so there are a lot of things that are measured in ranking, and there are business metrics, there are machine learning metrics. We will not talk about business metrics. Usually this is conversion, but there are a lot of them, like number of rate of the clicks, rate of conversions, rate of add to carts, if we're talking about marketplaces. This is also number of interactions on some websites. If we're talking about search engines, this is number of clicks on the websites, and so on, number of like follow-ups on different like pages and so forth. So what is MAP? MAP is mean average precision. At some K here in this example, it compares the average precision of a ranked list of items returned by system to some ground truth. So idea here is that we need to have some ideal ranking of the suggestions. How do we get this ideal ranking of the suggestions if we don't know, for example, what should we show to the user first, either broccoli or broth? Then we need to think about what suggestion was clicked more, or from what suggestion more relevant user signal was coming. And by that I was saying, okay, users which ordered something, they were clicking more on suggestion broccoli, for example. And here we say that broccoli then should stay first. And so, for example, if there are 5 suggestions that we want to show, then we say, okay, the first suggestion that should be here is the one that brought us the most purchases, or the most clicks on the website, or the most interactions with advertisements, or something like that. Precision of ranked list, it is defined as the ratio, so it is the ratio of number of relevant items to the number of items retrieved up to that rank, to that K. Average precision is when we average these precision ratings of all relevant items in the list. So usually MAP and DCG, which we will talk about now, they are both like implemented by the majority of packages in Python and in Scala as well. And DCG translates as normalized discounted cumulative gain. You can shortly say that it is DCG, which is discounted cumulative gain. It is just like averaged. It's another metric where we are taking into account relevance of an item and its position in the ranked list. So relevance score is assigned to like every item in the list that we ranked, and we discount the scores which have lower rank positions. So the idea behind this metric is that we are more happy when we place the first, for example, 2, 3 suggestions in the right order, rather than we place the last 3 suggestions in the correct order. So the better is the ranking of the first suggestion, the higher is NDCG. Yeah, and here we are also usually thinking that, okay, like the suggestion which has the most interaction, which brings us the most interactions, or the most purchases, or the most clicks, is the suggestion that we put first, then goes the second suggestion, and so on and so on. And then we can calculate NDCG based on this assumption. It really depends on what your business wants. So yeah, I think we are on almost 45 minutes now. Yeah, and to conclude, the last thing I probably want to say that, yeah, autocomplete is a system which like is very dependent on what your business needs, what your company needs, and it's also very dependent on engineering, where like engineering needs data science in a very tight place, because autocomplete is a customer facing service usually, and this is the thing where like your computer science knowledge, for example, for this WFSTs, it meets with engineering, where you need to think about the object and the approach which will give you the lowest latency, together with machine learning and data science knowledge, where you are thinking about how you should rank your suggestions. So this is on the intersection of all these things. This is also very dependable on business and on the requirements that you get from your business. But this is what's kind of interesting and kind of fun when you are working with it, because this is not just like, pure research where you are just, I don't know, looking for a better model, tuning your hyperparameters to get better scores, trying to get a lower loss and so on and so forth. This is where you are like hands-on working on different things simultaneously, and like considering this whole scope and trying to bring into your product not only for example like a very good ranking of results, but you're also thinking, okay, like we have results which are good ranked, but we also need to have a very good response time, a very small response time, and in the same time your retrieval, not only your ranking, should look very good. And yeah, at the same time you are thinking, okay, like this should be WFST, which WFST implementation should I take, which analyzer should I take, which analyzer will be faster, which will be slower, and so on. So yeah, there are a lot of things behind it, and yeah, it's not trivial, and it's fun to work with tasks like that. And yeah, I think we can go into questions if there are any.
Thank you, Galia, very much. So if someone have questions, you can ask it in chat, or you can unmute yourself and then ask. Don't be shy.
I've got a question, if possible.
Yeah, sure.
So thank you very much. Thank you very much for giving the talk. Like it's been really interesting. I wanted to ask about whether you've got any experience with competitors to Elasticsearch, such as Algolia or Millisearch. So we were using the previous startup I worked at. We used Algolia for a while, and then it got super expensive. So I had to rip it out and plug in Millisearch. And for our purposes, it actually did most of the stuff we wanted out of the box.
Yeah, like thank you for the question. Yeah, I haven't got a hands-on experience with like this specific engines. The only thing I can recall is that I was like very interested in Gina AI. I think this is a startup which like delivers smart neural search, as they call it. So this is a box where you get autocomplete, where you get like ranking, where you get, as they say, a very intelligent and very highly tunable and scalable search. And they do it all in Python, but in the same time they claim their latency is very good and like this is a very cool product, something like that. But yeah, at that time it was kind of on a bit early stage, but yeah, as far as I know, they're developing their product, but yeah, I wasn't working with that specific engines.
Yeah, it seems like a really sort of interesting field that's evolving quite quickly. I know Millisearch essentially jumped very quickly about 6 months ago and threw in a vector database backend, because I think they realized they're going to try and hack in semantic search based of a large language model in some way. And I mean, it's all continuing to evolve. It's super interesting. Yeah, that's my question. Thank you very much for the talk.